want to talk about one paper this year, which is joint work with my collaborators Denny Wu and Joan Bruna on propagation of chaos in two-layer neural networks. It's okay if you don't know any of those words, you will soon. So this talk is about very big neural networks, and in particular two-layer neural networks, so they look something like this. In this talk, we're going to look at very wide neural networks and infinitely wide neural networks, which are often called mean field neural networks. And a mean field neural network just means that it's a two-layer neural network where the number of neurons in it is infinite, and also the parameters are scaled in a certain regime. And so the main question of this talk is, does the behavior of a very wide neural network well approximate the behavior of an infinite width neural network? And when the answer to this question asymptotically is true, which you'll get a sense for what that means later, then formally this is called something called propagation of chaos, which is originally a term that was defined in the statistical physics field about particles in gases. Okay, so let me start by talking a little bit why we might care about these very wide or infinite width neural networks. So one reason is a lot of recent work on scaling laws. For example, this plot is from the work of Kaplan et al. Show that if we want to achieve a small loss, then we need to have a number of parameters in our neural networks that becomes very, very large. So in fact, they showed that you can see in this last plot that the loss scales inversely polynomially with the number of parameters in neural networks for certain natural language objectives. And usually the number of parameters in a neural network scales something like, usually the width in a neural network squares something like the square root of number of parameters. So we clearly want to understand what happened when the width grows really large. Another reason why it's important to understand neural networks that have infinite width is because it turns out understanding what happens in the limit can tell us practically how to do certain things like decide what our hyperparameters should be. So for example, this work of Greg Yang and his collaborators showed that if you want to understand what the optimal learning rate is for a very wide neural network, it turns out you don't have to train that hyperparameter, the learning rate, at the final scale that you want to understand, that you want to train your neural network at. You can actually learn the optimal learning rate for smaller neural networks. You see these different curves with 128, 256, et cetera, growing widths. And they all achieve the same local minimum, which is the best learning rate you could choose. And these phenomena being true is contingent on us having some understanding of what happens when the width of the network grows and does it achieve some limit, which is this main question of mine. Another reason we might care about these infinite width neural networks is analytically, it turns out they're much easier in some regimes to analyze than finite width neural networks. So in a normal two-layer neural network, if the input dimension of the neural network is d, and the number of neurons, the width, is m, then if we want to understand the dynamics of this neural network, typically we have to track d times m parameters, which corresponds to all the weights of the m different neurons in the neural network. In the mean field infinite width regime, it's possible, though, to model the network as a continuous distribution on the neurons. So what do I mean by this? Let's say the input dimension of the neural network is d. So in this example, d is 2. Then we can imagine the neurons as being some distribution over this two-dimensional space, since there are infinitely many of them. So they have a density, the neurons. And we can represent the output of the neural network as the expectation over drawing some neuron from this distribution, which in this case is a distribution over 2 dimensions, and evaluating the output of what that neuron drawn from the distribution will do from the input, and then taking the expectation of that. So if we think of infinite width neural networks in this way, as being represented by a distribution of neurons, then in order to understand the dynamics of these neural networks, all we have to do is track the evolution of this distribution. Now, a priori, that doesn't make things necessarily any easier. This distribution could be incredibly complex. But it turns out that in a lot of problems of interest, it might turn out that this distribution row has various symmetries which make it easier to analyze. So as an example, going to the case of a single index function, which is actually what Alex talked about before, let's say we're trying to learn this function f star of x equals some activation function applied to x projection in the E1 direction. So the E1 here is the W star from the last talk. So, okay. And let's say we're in this mean field regime. We're representing the neurons in the neural network by some distribution, rho. So if our neural network has infinite width, and this loss has certain symmetries, so in this case, the symmetries of the loss is that it only depends on this E1 direction, but in all other directions, everything is completely symmetric. There's no way that we could sort of distinguish from the population data the difference between, for example, the E2 direction and the E3 direction. Then it's possible to claim that this distribution that we're analyzing of the neurons is going to maintain certain rotationally invariant symmetries. So in this case, in all the dimensions besides the E1 dimension, it will have rotational symmetry. And so we can imagine that the distribution of these neurons in those other dimensions has a rotationally invariant distribution like this. And so instead of having to model this entire distribution, we can just think of it as its projection on a single direction, which in this case we'll care about its projection on the E1 direction, and everything else will be well defined if that's given. And we can just track the evolution of this one-dimensional distribution. Okay. So let's go back to the main question of this talk, which was, does the behavior of a very wide neural network mimic the behavior of an infinite width neural network? And I want to make this slightly more precise. A lot of people have shown that this is true in some extent. This neural network, when it becomes wide, it can approximate this well. But I want to understand this quantitatively. So if this neural network has to be exponentially wide in order for this comparison to hold, then it's not very useful to people who want to design real neural networks. So to refine this question, I want to understand whether the behavior of a polynomially wide neural network, where it's polynomial in the input dimension D, which is something that typically grows very large in practical machine learning applications. If the width is polynomial in this input dimension, we can have a close approximation between this finite width neural network and this infinite width neural network. Okay, and that's basically making this propagation of chaos phenomenon non-asymptotic, because I want to understand exactly the relationship between the approximation error and the input dimension D. Okay, so why is this tricky? So neural networks live in a non-convex landscape. And it turns out that when we do gradient descent on a neural network, and actually more in particular if we do gradient flow on the neural network, then it's actually doing gradient flow in this space, which is not the typical parameter space, but it's a space with a Wasserstein 1 geometry. It's okay if you don't understand this. All you need to understand is that when I'm running gradient descent dynamics on an infinite width neural network, it's descending in some loss landscape. And so I want to understand the difference between this mean field neural network, which has infinitely many neurons, and this finite width neural network, which just has m neurons. And so at initialization time, when I initialize the two neural networks, one is going to have infinitely many neurons, but the finite width one is going to have m neurons sampled from the same distribution as the initialization of the infinite width neural network. And so at time 0, since this is just m samples, it's actually easy to show that the functions represented by these two neural networks, assuming all the weights are bounded and a few things that I'm not going to say here, scales roughly like 1 over square root of m, where m is the number of neurons. This is sort of a standard Monte Carlo bound that you can get. And so the question is, if at initialization time these two neural networks are very close, how close are they going to be at some later time t? And so if this was in a convex landscape, things would actually be easy. If they started far away from each other, they would get closer. But in a non-convex landscape, the gap between these two neural networks, the width m1 and the infinite width one, can actually blow up exponentially. And the rate at which it blows up exponentially depends on the smoothness of this landscape. And so it's not so hard to prove this bound that's derived from Grunwald's inequality, which essentially tells us that the distance between this finite width neural network and the infinite neural network is going to be bounded by exponential in the amount of time we've been training for times the initial distance between these two networks. So we can get a bound that looks something like this, that bounds the distance between these two neural networks at time t. So this approach has been very useful in a lot of prior works, and they have in fact shown some version of an answer to the question we've been asking. So for example, the work of Song Mei and his collaborators in 2018 showed that for neural networks with bounded activation, you can achieve exactly this exponential in t divided by square root of m error. And so this was suffice to show useful comparison bounds to the mean field model for problems where the input dimension was order 1 and the time that you were training for was also order 1. They extended this along with Theo in 2019 to the case of unbounded activations, and their initial bound had some dependence on D, so it had to be constant. Here they were able to remove the dependence on D, and so they were able to show that there's an actual useful comparison between polynomial width neural networks and infinitely wide neural networks for problems that only took theta of 1 time to train for, which correspond actually to the class of problems that Alex introduced instead of information exponent 1 or leap exponent 1, so they only take a short amount of time to train for. This was applied in this staircase line of work that Alex talked about. So they were able to show that they could learn a large class of multi-index functions using this mean field method by showing exactly an approximation between the polynomial width network and an infinite width network. And in some work of my co-authors a couple years ago, we also extended this to some problems where the training time actually grew with D, but it only grew logarithmically with D. And so this was able to be applied to some information exponent 2 problems, which take a little bit longer to learn. And the way we did this was by breaking down this Gronwall bound and observing that this Lipschitzness is very non-uniform over the landscape, and replacing this L with a time-dependent version of L, which gave us a tighter bound using this Gronwall's inequality. But all of these approaches are fundamentally built on this Gronwall inequality. Okay, so what about the case when the training time is polynomial in D? So Alex in his previous talk didn't talk exactly about how long the training time is, but it turns out that in these gradient descent problems, typically the training time also has something to do with the information exponent or the generative exponent. So for single index models with high information or generative exponent, for example, something like this, like Alex showed on his plots, when this activation is very challenging, it might take polynomial in D time to learn. And also for problems like learning parities, where the number of terms in the parity is large, this could grow polynomially in D, the training time. Okay, so the main sort of technical question behind this work is, can we improve on this Gronwall bound to remove this exponential dependence in T so that we can actually get a useful approximation between infinite width neural networks and finite width neural networks, even when T grows polynomially in the dimension D. So here, I don't know why I wrote epsilon m. This should be like 1 over square root of m. But you can see if this is going to grow exponentially in the training time T, and T is polynomial in D, you'd have to have m be exponentially large in D for this bound to be useful. So I wanted to try to understand if we could possibly remove that exponential dependence. Okay, so now it's going to get a little bit technical, if it hasn't already been. So the way this Gronwall bound is built in a little bit more of a technical way is that we compare two things. So we look at two different neural networks. One is our width m neural network, and one is the infinite width neural network. And we make a certain coupling between these neural networks. So we map every neuron in this width m neural network to a neuron in this infinite width neural network. And the way we create that mapping, so that's the up in the box there, that's the WIT is the ith neuron in this m width neural network at time t. And then WIT mean field is the location of that same neuron. So the neuron that was initialized at the same spot at time 0. So maybe it was initialized in the E1 direction at time 0. And now we look at where that neuron is located at time t if it had been evolving in this infinite width mean field dynamics. And we call the distance between these two neurons delta ti. So that's the distance between the ith neuron in the finite width neural network and the ith neuron in the infinite width neural network at time t. And so by introducing this notion, this coupling, it's possible to bound the distance between this finite width neural network, rho hat m, and the infinite width neural network, rho mean field, in 2 steps via the triangle inequality. So I'm going to bound this by the distance between the finite width neural network and this rho hat of m. And the rho hat of m is as if I just took these m neurons that were coupled with these neurons, but from the mean field distribution. So that's going to be some different neural network. Yes?
Sorry, maybe you said it and I missed it, but what's the mean y for the mean field of the neural network?
So it's just, it's a good question. It doesn't really make sense what I is. But what I'm saying is I have this infinite width neural network. I sample m of these neurons. I label them 1, 2, 3, 4, all the way up to m. And now I look at the mean field model, and that's corresponding to, I mean, there are infinitely many of those neurons, but I'm going to map them to exactly the ones that have the same initialization. I'm going to call those 1s, 2, 3, 4, all the way up to m. So I'm just going to label like m of them in here. And the way I'm going to choose if I'm going to label them is if they appear here at time 0. So like if I drew some neuron at time 0 that is in the E1 direction, I'm going to look at the neuron in the E1 direction here and call that neuron 1, and I'm going to see where it evolves. It might not evolve in the same way as that one, but they have to be equal at time 0. Yes, I only track m of these. Exactly.
So the error accumulates in such a way that it's still small.
So what's going to happen is I'm going to call rho bar m the distribution on these m things I'm tracking. So I have 3 things, okay? I have rho hat, which is the distribution of these m things in the real empirical neural network. I have rho bar, which is the distribution of these m coupled neurons, but they're sort of in this different dynamics. And then I have the distribution rho mean field, and that is the distribution of this whole thing. So I have 3 different things. And the only point that I was trying to put here on the bottom is exactly that, is that I can bound this difference between the rho hat, which is the thing I really care about, and the infinite width one, by looking at this 2-step decomposition, the difference between this rho bar one, which is these m coupled neurons, and then the distance between the rho bar and the infinite width. And so actually, this breaks into 2 terms. So the second term we'll talk about first, the distance between these m sampled neurons and this infinite width one, this actually just scales like 1 over square root of m. And it's easy to see that because these m neurons at any time t are actually just an IID sample from this infinite width thing. So it's going to scale like 1 over m, this error. And then this one is going to scale something, it's going to have to do with these distances, this coupling error between the ith neuron here and the ith neuron there. So if the distance between them is I, it turns out that the distance between these whole distributions in function space is something like the expectation over these I different neurons of that distance. So that's sort of like this empirical error. Okay. Okay, so let's understand how fast these delta i's grow, right? So if we want to understand like how fast the distance between the finite width and the infinite width one grows, I have to understand how fast these delta t's grow. And so to do that, I want to introduce this thing that I've been calling the local landscape, which is formally the first variation of the loss at a certain neuron in the neural network. It's okay if you don't understand that. What is this? So what I'm calling the local landscape is if you just look at one neuron, fix one neuron in your neural network, in your infinite width neural network, and then fix everything around, all the other neurons, and look at what the landscape is if you just vary this one neuron. So it's this red line. So this is all of parameter space, and then the red line is just saying, I'm looking along the axis of this one neuron. What happens when I move it a little to the left, a little bit to the right, a little bit in this direction? It's going to affect the loss in one way, some way. So that's the red line. That's the local landscape. And when I train via gradient descent or gradient flow, there's a certain velocity field induced, and the velocity field induced is the way that the neurons move. And this is actually the gradient of this local landscape. It's easy to derive this if you write down gradient descent. And so each neuron moves in the mean field according to this velocity field. And so if we want to understand how this delta t grows, we need to understand the difference between how much the mean field neuron moves and how much the neuron moves in the finite dynamics. And so basically, the rate of change in this delta ti, the distance between these two neurons, is going to have to do with the difference between what happens when I plug in the mean field neuron and the mean field neural network into here versus if I plug in the neuron wi, which is the neuron in the finite width dynamics, and I plug in, instead of rho t mean field, I plug in rho hat, the actual finite width neural network, into this velocity field. And so there are sort of two error terms that come from plugging in wi instead of wti mean field, and from plugging in the rho hat instead of rho. And so these are the two terms. One is the term that you get from the distance between wi and wi mean field. So there's going to be a gap that sort of scales with delta ti, right? So if there's a big gap between what I plug in this coordinate, then there's going to be a gap between what comes out in the velocity. And the second term is a term that scales with the distance between these two distributions. So in order to understand the dynamics of these delta t's, basically it grows something like the size of this delta t. So it's like this exponential growth. And then also it scales like the size of the average distance between this rho hat and this rho mean field. Okay, and it's possible to bound it in this way by looking at the maximum of the delta t's. And so basically from this sort of intuition, you get the rate of change of the delta ti's grows something like proportionally to the maximum of the existing delta ti's. So you can see from this that if this velocity field v has Lipschitz L, then you're going to get an exponential in L growth of these delta ti's. So that's basically what's going on under the hood behind the Gronwall bound. Okay, so remember we were trying to understand whether this Gronwall bound is tight, right? Like whether we can do something better than just naively using this equation. Okay, I want to give an example from a problem that motivated a lot of this work, which is the problem of learning, I guess I didn't write it down, but this is the problem of learning a single index model in a neural network with information exponent 4. Okay, so this is a problem that's pretty hard because it has a high information exponent, so it takes a lot of time to learn. And it turns out when you look at the dynamics of this problem, this is a plot of all the different neurons at the different times and how far they're aligning with the ground truth direction W star. You can see that all of them are sort of escaping a saddle and converging towards the direction W star at very different times. And because of this, it turns out that the curvature of their local landscape is very varied in time. And also, empirically, the distance of these neurons from the distance of their counterpart in the mean field is going to blow up and go down at very different times. So why am I showing you this? The reason I'm showing you this is that I'm saying that if we use this, this coupling error dynamics above, it's very, very loose because it's plugging in the maximum of these delta t's at every time. But in fact, these delta t's are very, very varied among the neurons. And so this is a very, very loose approximation if we're using the maximum at every time. So the key kind of intuition behind this work is to try to understand, can we, instead of using sort of the global Lipschitzness of this problem and these worst case bounds, can we try to understand how this error blows up on a neuron by neuron basis and use the fact that each neuron has certain properties going on in its local landscape and leverage those properties. Okay. So let me state our results with that. Okay, so, here's another version of our main question, which is, can we show under some conditions that the distance between this infinite width neural network and this finite neural network is bounded polynomially in the input dimension t and the training time over the square root of m? Okay, and so we answer this question in a certain setting. So let me set it up for you. So as I've mentioned, we're studying a 2-layer neural network where the second layer weights are all fixed to be 1 in the 2-layer neural network. So the function just looks like this. We're going to be in a teacher-student setting, which means that we're trying to learn a function F star, which can also be represented by a neural network with the same activation function, sigma. And that teacher neural network has finitely many neurons in it. Oh, actually, I didn't say that here. I'm going to say it on the next slide. But yeah, it has finitely many neurons. So this distribution rho star is atomic. And the training dynamics I'm going to be looking at is training this neural network via projected gradient flow, which just means that at every which means that every neuron is moving in the direction of the gradient of the loss, the square loss. But also at every time, I'm projecting those neurons to stay on the sphere. So all these neurons Wi are always going to have norm 1. OK, so this is the setting. And our main result is that in this setting, suppose a certain set of assumptions hold, which I'm about to flash, but I don't want to overwhelm you guys. So suppose a certain set of assumptions hold up to time t. Then with high probability over the initialization of the neural network, so I'm choosing these m random neurons to start with, the distance between this finite width neural network and this infinite width neural network is bounded by t times the training time squared divided by m times this j max thing, which is a certain stability parameter I'm going to introduce in a minute. And we can also show that if the neural network is trained on, instead of being trained on the population loss, it's only trained on n different samples, then we just have to also incur this term of n in the denominator, and we can bound the difference between the dynamics of the infinite width neural network trained with infinite data and the finite width neural network trained with finite data by this polynomial over the min of m and n. So m is the number of neurons, n is the number of data points. OK, so what are the assumptions? I'm going to talk about a few of them in more detail, but just at a very, very high level. One is that we make this assumption called local strong convexity, which is a property on the local landscapes about them being strongly convex in certain regions. The second thing is this J max thing, and this has to do with the instability of certain particles in the local landscape. So it's another property on the local landscape. I'm going to get into it more. The other condition is an average stability condition, which has something to do with the stability of certain particles relative to other particles. And then there are a few technical conditions. OK, so the second main result in our paper is that we apply this theorem to the case of learning these single index functions. So we show that if there's a ground truth function that's some high information exponent single index function that we're learning, so for example, that's a problem that takes polynomially in d time to learn, then we show that after a certain polynomial in d time, the loss is less than delta for any delta you choose. And similarly, as long as the width is more than this polynomial d to the c k star, where k star is the information exponent, we're able to show that the distance between this finite width neural network and infinite width neural network is smaller than delta squared. Okay, and here are some plots which also show this. So the first one is the prediction risk of the neural network. So we show that it's actually learning in this amount of time. And then we also plot this, this function error, which is the difference between the infinite width neural network and the finite width one multiplied by m for different widths. And so you can see that this thing roughly scales like 1 over m, because when I multiply it by m, all these lines roughly coincide. And the other thing we plot is these delta TIs, which is our analysis tool. So this also exhibits similar behavior, which is when you, every time you double the width, you 1 over m times this error. Okay. Okay, so I want to say a little bit more about the assumptions, specifically this stability thing, which appears in our proof. Okay, I'm going to actually skip this. It's not important. Okay, so one of the conditions I said is that this property called the local stability is bound, or this maximum, this J max, is bounded polynomially in T. In order for this final result to be polynomial in D and T, this stability has to be. So what does this stability say? It means that if I look at the local landscape, okay, sorry, I was talking about the wrong assumption. Okay, so the first condition that I had was this local strong convexity assumption. And so the local strong convexity assumption says that if we look at the local landscape, which I said is what happens when we fix all the neurons in the neural network besides one and just look at how the loss changes with that one neuron. The condition we need is that when this neuron is near one of the teacher neurons, so the teacher neurons are the neurons we're trying to learn, then this landscape looks strongly convex. So the dynamics ends up looking something like this, where in this picture, here are the two teacher neurons. They're at the side of this circle, and you can see all the neurons are being sucked into there. So this local strong convexity is basically this property that when you get close to a teacher neuron, you get sucked in. Okay, and there's a formal version of it, which I won't go over. And then the other condition I wanted to talk about is this worst case stability condition, Jmax, which we also need to be small if we want our results to be useful. So the stability parameter Jmax basically says also, if you look at this local landscape, so this red line, which I've now plotted as this red line, you can define the stability of it as what happens if you take two particles in this local landscape, you perturb one of them a tiny amount from the other one. So I have this yellow one, and then the green is a slight perturbation. And then I let them flow in this like gradient descent dynamics on this local landscape. And I look at how much the gap between the yellow one and the green one blows up. So you see as they go down the hill, the distance between them gets a little bit bigger. So I call the stability at time s to t to be the quotient between their distance at time t and their distance at time s. So the stability is going to be very bad if the distance between these two particles is going to blow up a lot. And so this is the formal thing, which you don't need to understand, but the Jmax parameter is an upper bound on the maximum value in any one of these local landscapes of this worst case stability between some time t and some time s. So how much the gap between these particles can blow up. And I want to show just one tidbit of our proof, which is some intuition for why this local stability parameter doesn't get too big in problems that we care about. Okay, so remember the stability is the distance between these particles at some later time t and the distance between the particles at some previous time s. And so there's this observation that you can make about settings where this red local landscape is one-dimensional, which is essentially the intuition that we use in our whole paper, which is that this quotient between their distance at time t and their distance at time s is the same as the quotient between the velocity of the particle at time t and the velocity of the particle at time s. So why is this the case? If you wanted to understand the gap in distance between this yellow and green particle, you want to understand how much forward in time this green particle is ahead of this yellow particle. Right? So at the beginning, they're near each other, they're next to each other near the top, but I've pushed the green particle ahead a little bit, and I can think of it as pushing it ahead a little bit, not in space, but actually in time. And so when you sort of start to make these comparisons between space and time, you get that the distance, the quotient in the distances can be bounded by the quotients in their velocity. And for certain problems we care about, for example, the problem that I showed an application for, this single index model, it's possible to show that the velocity at any time scales something like polynomially in the projection of the neuron onto the W star direction. Okay? And this is sort of a standard computation for single index models. But importantly, this thing never becomes bigger than 1. Okay? Even if it's fully aligned with the W star, the velocity will always at most be 1. And the other thing is because we always initialize a little bit away from the saddle just by randomness, the velocity is always bounded by like 1 over square root of d to the power of some polynomial. So this quotient is never going to be too large. I'll just stay there for a second. Yeah, so this is basically the intuition for what's going on in the local landscape. And I said to you earlier that one of the key ideas of our proof was trying to break things down and not look at like the global Lipschitzness of the problem and bound everything in the worst case, but to break things down and look at how the error grows for individual neurons one at a time. And so the two key ways we're doing that is we're looking at this local stability, so we're understanding the stability of this local landscape. And the other way is that we're using this fact that as the neurons converge, the local landscapes become convex. And as you can see, the convexity of this neural network would make these two particles contract. This green and this yellow particle. Okay. So I'm going to skip the rest of this because it's not that important. Five more minutes of talking? Oh, okay. Sorry, I just saw the time was 10:30. So.
No, but it's no.
Okay. I'll say one more thing then about the proof, which is that okay. So this equation probably looks very unfamiliar, but the key idea is we're trying to understand the dynamics of this delta Ti, which remember is the distance between the neuron in the with M neural network and the neuron that it's coupled to in the infinite width neural network. And it blows up for two reasons. One is because when I was plugging into the velocity field, there's a difference between these two neurons, Wi and Wi mean field. And the other is there's a difference between the distributions of all the other neurons. So one is this local term, and one is this interaction term. And so I spent a lot of time in the last two slides talking about like this local error and how this local error will change and the stability and what happens as you converge in this landscape. The second big piece that I didn't talk about at all is the interactions of the neurons in the neural network and how they influence this gap between the finite width neural network and the infinite width neural network growing. And so the key observation is that the dynamics induced by the interaction terms is actually given by a positive semi-definite matrix. And that's because all the neurons in the neural network are repelling each other. So that basically means that like on an intuitive level, if the neurons are repelling each other and one neuron gets slightly off course, then the other neurons will actually push that neuron back to be back more on course because they're repelling each other. So they actually help each other stay on course if they deviate from the mean field dynamics. So this interaction Hessian is actually a really good term for us. It turns out it's a positive semi-definite matrix because of this repulsion, and so that actually makes the neurons stay on course. So the interaction term is good. It's PSD, and it causes these neurons to go back to where they belong. And so one of the like the main challenges in our work after we've made these two observations is figuring out how to deal with these two sort of good things together, because it turns out when they interact, things get very complicated. I won't say more. Okay. Okay, so let me just finish with like a few future directions. So in this work, we showed how to prove a tight connection between a finite width neural network and an infinite width mean field neural network, but we did it under many different assumptions. And one of the key assumptions we had was this assumption that the teacher function that we're learning is represented by finitely many neurons. It was an atomic distribution. And so that's very limited in terms of what we can achieve with a neural network. It means that we can only learn finite width neural networks. But in reality, as we said at the beginning with like scaling laws, et cetera, we really care about learning functions that are complicated and need to be represented by many more neurons. And so a key question is, can we extend this result to the case where the teacher function is not atomic, but it actually lies on a manifold and it requires infinitely many neurons to represent? And this would cover the case of learning misspecified single index models, for example, which is when we don't know the link function. And a more general question I have is like, if we're learning general multi-index models like Alex spoke about earlier, do we expect to have this propagation of chaos phenomena or not? Because right now our proofs don't extend to that case, but it would be very interesting and potentially help us analyze those complicated problems. That's it. Yeah.
Great, thank you very much. We have time for a couple of questions, and like I said, I'll start at the back. Or maybe I'll start with one of my own questions. Oh, sorry, did I miss one? Ah, okay.
Thank you. I was curious about your result when you gave us the theorem. You had one result for like the finite sample case where with finite samples, you showed basically that increasing the number of neurons does not really help, right? Because you had this minimum between the number of samples and the
Yes.
number of neurons. Can you just comment a bit further? Is it due to some collapse phenomenon where all the neurons start doing the same because?
No, I think this is just a limitation of the theorem. So it's in that theorem. I'll go back to it for a second. So in this theorem, what I'm showing the distance between is two objects. One is a finite width, m-width neural network trained with n data samples, and the second one is an infinite width neural network trained with infinite data samples. And so all I'm saying is that the distance between these two is governed by the maximum distance incurred by the finite samples and the finite width. So the maximum in distance is going to turn into a minimum in the denominator. So it's not so complicated or interesting. Yeah. I think.
So yeah, thanks for the talk. Very nice. Nice to see the extended version of the talk. I have a question concerning this theorem. Actually, you mentioned it at the end. I don't see in these bounds the dependency on the potential width of the teacher or the number of atoms that is contained in the teacher. How would it depend? Where is it encoded?
Okay, I'm trying to remember if I have the exact dependence. So we assume that just the number of teacher neurons is, wait, no, actually we don't assume that it has to be finite, but okay. There's no dependence, but there's dependence on another parameter, which is the thing that ends up mattering is the rank of the kernel matrix induced by the teacher neurons, okay? So the teacher neurons induce some kernel matrix, and if these neurons, if they're supported in if they're in a low-dimensional space, and the activation function of the network is a low-degree polynomial, then the kernel matrix is going to be low rank. So actually what comes out is a dependence on the rank of that matrix. So you could have many neurons, but as long as they're in a low-dimensional space and the activations applying to them are polynomial, it's okay. If there would be a dependence on like the rank of the subspace that these teacher neurons lie in. Yeah.
Going maybe in a similar direction, I was wondering, so for a while I was very interested in sort of similar bounds, if you will, comparing basically the dynamics of an actual neural network and then what you would get from integrating some ordinary differential equations that describe the learning dynamics, in terms of some kind of order parameters, right?
Okay.
And so there, usually, you also get bounds a little bit like this, and through some kind of propagation of chaos arguments, you always have this exponential term in the time. You can get some nice dependencies on the learning rates, the width, etc. But this exponential in the time of the dynamics, that's always there, and it's always kind of a bit of a pain. Like,
wait, sorry, I think I missed. What is the setting in which you also have this exponential in time dependence?
Like when you're trying to analyze, you have your actual SG dynamics on actual of an actual neural network, right? That's some kind of Markov process.
Yeah.
Let's do some kind of online learning. And then you can derive a description of those dynamics in terms of ordinary differential equations, right? For a number of order parameters or sufficient statistics, right? And then you ask, okay, for how long is this description actually correct? And so
yes.
the proofs that we have, they always have this exponential depends. I think people agree that these descriptions are probably valid for much longer, but could you use your tools?
I don't know. I'm like very curious to like look into that. Like I don't know. Like for example, for like AMP or something, you're saying maybe or like.
Yeah, or even just stochastic gradient descent, like.
Yeah. I think. I don't know. I'm very curious about that. I don't know the answers. So the key here ended up being like writing down instead of just saying everything grows exponentially, writing down like the exact dynamics of like what matrices are involved in the dynamics of these error terms. And so I think like you would have to do the same for those problems. You would have to write down the precise error dynamics and then try to understand if the matrices in that dynamics have any special properties. Like maybe they have some, maybe they're PSD, maybe something. I don't know. Yeah, I just don't know. But I'd be hopeful that maybe there's some structure there, but you would have to like try to exploit the structure. I don't know.
Only a question from the back.
Thank you for your talk. My question is, I'm curious how long these finite networks stay close to the mean field dynamics before the deviation became significant. So is there any threshold till which we can compare these two networks and then the deviation are so significant that we can't compare this finite dynamics with the infinite networks?
I don't know. Obviously, that's sort of what this talk is about. I can tell you that I did some experiments. Sorry, that's what I'm just trying to get to.
Because I think this mean field network is just a mathematical convenience to prove the things, but not just we can't. We must have some threshold or some width, some length after which we can't compare these two.
Yeah, so I don't know where the limit is. Like if I did, then I would tell you all the answers in this talk. But I can tell you that we did some simulations on various different problems, which I've listed here. So for example, like learning like these like XOR problems and all sorts of different things. And in all of the problems, even though our proof tools were like completely limited and we couldn't prove anything about this full set of problems, all of them exhibited this same phenomenon, which I showed before, which just look at this plot, for example, which is where when I plot the deviation from the mean field scaled up by a factor of n, all of these lines kind of coincide. So you seem to get these like 1/m rates, even when m wasn't that large, like when it was like 4,096, and I think these plots even like extended smaller than this, but I didn't show it. So I think like in actuality, things seem to be close to the mean field for way longer than I would have expected. I don't know how to prove that, obviously, but all the experiments, I tried very hard to come up with the experiment where they deviated. I couldn't find a single case where it deviated, so I don't know.
All right. Let's close it here and let's leave the rest of the discussion for the coffee break upstairs. It's waiting for us. Thank you very much, Margalit.